Hello and welcome to Physical Attraction, and today we're going to be talking about the laws of thermodynamics. So thermo is a prefix that means temperature and heat, and dynamics is the study of how something moves when it's forced or indeed sometimes unforced, but usually with dynamics there are forces involved. So this is about the flow of heat, broadly. But there are profound consequences for how we think about ideas like energy and even information as well. But first, this episode's physics-based chat-up line. Because these ones are awful, even by my usual standards, I'm going to give you a few to choose from. You must store a lot of internal energy because you're looking pretty hot. Let's convert our chemical potential energy to sound and heat, if you know what I mean. They say that perpetual motion is impossible, but we'll give it a go. So there you go, feel free to deploy those at your leisure, and feel the sweet stinging heat of the tears rolling down your face as you're rejected once again. I should point out that although we enjoy coming up with these incredibly lame physics-based puns, Physical Attraction has a very sanguine attitude towards the actual use of these lines in conversation. If that's the best thing you can find to talk about with someone, well, you're kind of showing your hand already, aren't you? And in that case, they're well within their rights to tell you to go away. So now that we've moved from the hairy world of romantic interactions, we'll be talking about the laws of thermodynamics. So the laws of thermodynamics are basically statements about how energy behaves, and effectively they define what things like heat and temperature are. I think we all have this idea that we have a sense of what heat is and what temperature is, but nailing that down to a proper, consistent scientific definition is not easy. So the thermodynamic laws are incredibly useful because they describe natural processes, but they also allow us to calculate upper theoretical limits. Most systems that we know of ruthlessly obey the laws of thermodynamics, such that whenever anyone tells you that they've created a machine that violates them, you usually know they're wrong straight away. Now, the original descriptions of some of the laws of thermodynamics were in terms of heat engines, and the field of thermodynamics is incredibly important in terms of engineering the world around us. But they can also be applied to systems on the largest possible scale, including the universe itself. So from heat engines to the universe, the laws of thermodynamics, they're examples of this wonderful principle in physics of homogeneity, which means you can go anywhere in the universe and expect the laws of physics to be behaved in more or less the same way. And this is a Copernican principle, a principle that we're not really special, that there's nothing particularly unique about this region of space that we're in, except perhaps the fact that we happen to occupy it. And it's this, really, beyond so many other things in physics, that allows you to say, I'm going to do some experiments here on Earth, and I'm going to infer what's happening billions of light years away, based on those experiments. I'm going to infer what's happening billions of years ago, based on those experiments. And the only reason that's valid is because we assume that the laws of physics are obeyed everywhere. One of those fascinating universe-type calculations I came across the other day for the laws of thermodynamics that I wanted to share with you before we got into it. So Stuart Armstrong at the Future of Humanity Institute, he used thermodynamics to try and come up with a solution to the Fermi paradox. And you'll remember that the Fermi paradox is this question of, if there are aliens out there, if there are alien civilizations out there, how come they haven't talked to us? Well, in Stuart's reasoning, he seems to think that there's a very good reason, which is that the universe is expanding and getting colder and colder. And as the universe gets colder and colder, for reasons that we'll come on to, computation gets more and more efficient. And if computation is more efficient, it means with the same amount of energy, you can do more calculations. So he predicts that highly advanced alien civilizations would see a benefit in sort of hibernating through the warm period of the universe, waiting until things get cold enough for them to efficiently perform their calculations. And he can use thermodynamic laws to show that their calculations would actually be trillions and trillions of times more efficient, 10 to the 30 times more efficient, if they wait until the end of the universe than they are at the moment. So it's a very interesting concept. So on to the laws. I've named this series of episodes after a mnemonic for the laws of thermodynamics, which goes like this. You can't win, you can't break even, and you can't get out of the game. It makes it sound like you're playing a pretty unfair, loaded game, right? But we're all used to that. I mean, Leonard Cohen told us that, right? Everybody knows. So this corresponds to the first, second, and third laws, But actually there's a zeroth law that we need to cover briefly. It was kind of added on afterwards, which is why the numbering system is so messed up, but it's still important. So the zeroth law of thermodynamics basically defines what temperature is. It's what you measure with a thermometer. And what's a thermometer? Well, it's something that measures temperature. Okay, so you can see that we've got a little bit of a circular definition here. We all have an intuitive idea, I think, that temperature is kind of a measure of hotness, if you will. And microscopically, you can talk about temperature as being how much energy the molecules that make up a substance have. If the substance has low internal energy, then the molecules won't vibrate very much. If it has high internal energy, they'll jiggle about like mad. But this isn't a universal definition of temperature. So the zeroth law says that if two thermodynamic systems are each in thermal equilibrium with a third, then they must be in thermal equilibrium with each other. So if A equals C and B equals C, then A must equal B in terms of thermodynamic equilibrium. That might seem obvious, but you'll actually see that we've sneakily introduced all kinds of crazy terminology here. So back up. What's a system? What's thermal equilibrium? And why does this seemingly trivial statement matter? So in thermodynamics, a system is a region of space that you can describe by specifying a certain number of physical quantities. So maybe it's the air in a jar. Maybe it's the universe itself. The idea is that you can say, this region of space has a certain temperature, a certain pressure, a certain amount of internal energy, and it occupies a certain volume. So we call these state variables. They basically tell you what state your system is in. There are walls, real or imaginary, around the system, so that you can say, right, within this region the temperature has such and such a value, the energy has such and such a value, it occupies a certain volume, pressure, this kind of thing. And these things are well defined. It makes sense to talk about what they are. So you can talk about, for example, does it make sense to talk about the pressure of a single particle, or the volume occupied by a single particle? Not really, but for a thermodynamic system you can make more reasonable approximations. An open system lets matter, stuff, flow in and out. So maybe you can imagine a bucket with an open top. A closed system doesn't let matter flow in and out, but heat can flow in and out of the boundaries. So maybe a bottle of water is a good approximation for a closed system. Matter isn't flowing in and out, but heat can flow through. And an isolated system doesn't let heat or matter flow in or out, kind of like how your thermos coffee flask is supposed to work in an ideal world. And maybe, we don't know but it's conjectured, maybe the universe is an isolated system, thermodynamically. There's no inflow or outflow of matter or heat from neighbouring universes. Difficult to say for sure, but this is the approximation that we often make. When two systems are connected, but in thermal equilibrium, it means that heat, energy, isn't flowing between them. So imagine taking a jar of cold air out of a freezer. Now the jar system is in contact with the system of the room that you're in. Heat will flow into the jar from outside, obeying the laws of thermodynamics. Eventually, they come to equilibrium, balance, after the cold air has heated up to the temperature of the room. If you leave it long enough, they'll be at the same temperature, and then no heat is flowing. Heat could still flow between them, the jar and the room are still connected, but because they're at the same temperature, no net heat does flow between them. They are now in thermal equilibrium, balance. So in a sense, the balance is between the balance that flows from the jar into the room and the room into the jar. There might be some heat exchange, but it perfectly cancels out. So this is why the zeroth law actually defines what a temperature is. If you say that, regardless of what your substances are made of, regardless of what they are, how big they are, if you have two systems, each in equilibrium with a third, they will also be in equilibrium with each other. Which makes sense. Imagine if you have two objects in the same room at the same temperature. Maybe you've got a jar of air in one hand and a ball in the other. Well, they're both in equilibrium with the room. They're not necessarily touching each other, but you wouldn't suddenly expect them to transfer heat energy between each other when you put them together. So then we can say that this actually defines temperature. There is a quantity called temperature. Bodies can have a certain temperature, and if they're at the same temperature, regardless of what they are, no heat flows between them. That's the zeroth law. And you can basically summarise it as saying thermometers work. When you put a thermometer in your hand, or use it to take someone's temperature, you wait for the thermometer to come into thermal equilibrium with the thing you're measuring. So the fact that this thermal equilibrium exists, and is consistent between different pairs of bodies, that lets you measure temperature. It might seem like this is all a little bit pedantic, but actually the definition of temperature is very confusing and very concerning, and without this, it's very difficult to come up with anything that's physically consistent. Just a quick aside then about physical measurements of temperature. As so often in science, we're sometimes lumbered with units and terms that exist for historical reasons, but don't really make sense anymore. So it's with a heavy heart that I say, I'm sorry, Americans, but Fahrenheit is a terrible scale. You know, it was based on nothing particularly special. 0 degrees Fahrenheit is the coldest temperature that Mr. Fahrenheit could get to, the air temperature of his hometown. 96 degrees Fahrenheit was just his body temperature, the warmest temperature he could get. He chose 96 so that he could make a nice number of marks on his thermometer. These units are very idiosyncratic, they make no sense. There's no good way of defining them, and they're not useful in calculations. People say that Fahrenheit is better for weather because 0 to 100 degrees Fahrenheit is kind of like the range of temperatures on Earth. But this is really just an excuse. It basically means that we're used to it and we can't be bothered to change now. Anyone who's used to Celsius for a while will be able to tell you what 30 degrees, 20 degrees, 10 degrees or 0 degrees feels like. No one is so sensitive that they need a more precise scale and can tell the difference between, say, 71 Fahrenheit and 72 Fahrenheit. No one can even really tell the difference across a Celsius degree, so it's perfectly fine. Celsius is a little bit better because it's based on degrees that we can all agree on, that you can actually measure without needing the body of Mr. Fahrenheit or the hometown of Mr. Fahrenheit. Water is pretty common on Earth. It freezes at 0 and it boils at 100. The scale makes sense, it's nice and decimal, and it's based on physics. It's time to join the rest of the world and use a scale that makes sense. It doesn't have to be difficult. Or accept that it's not better and you're just being stubborn and backwards, and I guess we have to leave it at that. But Kelvin is the best, though. When the first scales were invented, people didn't realise that there was a minimum temperature, but now we do. The Kelvin scale takes this into account and starts at this absolute 0, the minimum of temperature. And this means that you can directly relate it to the energy that you're talking about. So whenever physicists do calculations, they use Kelvin, and they only convert to Celsius or Fahrenheit to talk about the weather or to impress non-scientists. Okay, rant over. So what's happening on the microscopic scale when things come into thermal equilibrium with each other? Imagine a box filled with air. You have to do a lot of imagining in thermodynamics. In the box, air molecules are bouncing around. They travel at different speeds, collide with the walls and each other, and when they collide they exchange energy. The collisions with the wall are what means that the gas exerts pressure on the wall. They're constantly pushing on the wall, which pushes back on them and causes them to bounce back. Some of the gas molecules will get lucky, and they'll have lots of collisions that add to their momentum, so they'll be travelling quickly. Others will be travelling very slowly until they get kicked by a faster molecule. So in the box you have a big distribution, you have a range of speeds. And in fact this distribution is a special function when things are in thermal equilibrium. It's usually called the Maxwellian, and you can look up the shape of this function if you like, it's very interesting. But for a system in thermal equilibrium, you can define a certain average energy that the molecules have. Some will be faster, some will be slower, but there will be an overall average. And this average is related to the temperature. If you heat the gas from the outside, maybe by putting a box on the stove, the average energy goes up. The temperature of the gas is increased, and so the molecules are moving faster. Now imagine that we inject a little bit of hotter gas into the gas in the box. The hotter gas molecules are moving around faster than the rest of the gas in the box. And these hot molecules will bash into the colder molecules, transferring energy when they do so. The way collisions work is that energy is usually transferred from the fast-moving to the slow-moving object. We know this from the world around us. Initially, this system is not in thermal equilibrium. That's because there's a section of gas that's at different temperature to the rest. So if you take the box on the whole system, it exerts more pressure on the walls, this gas, because the molecules of gas are hitting the walls more quickly. Because it's not in equilibrium, the system as a whole, we can't tell you the state of it. It doesn't just have one temperature or one pressure. It varies when you move from place to place. But very soon these new molecules will collide with the old ones and give up some of their energy. The temperature of the gas overall will slightly increase as this new energy spreads around the whole population. It's a little bit like how trickle-down economics is supposed to work. A few rich people show up and gradually spread their wealth around until everyone has some. And soon the system will be in equilibrium again, at a new temperature and pressure. Do collisions stop? No, the molecules are still colliding. Sometimes some energy will go to the newer molecules, sometimes it will flow to the older ones, but the system as a whole is still in equilibrium. The energies are all mixed up. If you put a thermometer in the gas, doesn't matter where, it would settle quickly to a specific temperature. It's the same when two bigger systems are in equilibrium. Their molecules might hit each other, giving each other energy, but overall, there's no net transfer of energy. No flow of heat. Nothing really changes. So there we go, the zeroth law. The first law of thermodynamics is the one that says you can't win. And this essentially says that energy is conserved for thermodynamic systems. You probably already know that energy can't be made or destroyed, only converted into other forms. So when you burn a fuel, say, you're converting energy that's stored in chemical bonds into, when it reacts with oxygen, heat, light, that kind of thing. This is a fundamental law that applies to all of physics, so much that energy conservation is usually the first thing physicists try to write down an equation for when they're faced with a new problem, because this is the one thing that we're really confident has to happen. Energy can change from form to form, and it can move around, but you can't make it or lose it. So for this, we need to go back to our definition of a system. The first law basically says that energy in a thermodynamic system can be in three forms: internal energy, heat, and work. And it says that the change in internal energy in the system is the same as the heat supplied to the system, plus the work done on the system. Work in physics is a force applied across a distance. It's a mechanical transfer of energy. So when you lift an apple, you're doing work on that apple against the force of gravity. When a car moves along a rough surface, its engine is doing work against the force of friction. Even when you're at work, and you're pressing down on the keys, your fingers are doing work against the spring mechanisms in the keys. So let's think about our gas box again. If you can push a valve to compress the box of gas like a plunger, you're applying a force. The force acts against the pressure of the gas molecules on the box, and it moves the valve across a certain distance. So when you push the valve, you're doing work on the system and giving it energy, and in this idealised situation, you can calculate how much energy you're giving it based on the pressure. The first law of thermodynamics says that the internal energy, the energy of the gas molecules in the box that we can talk about, it can change by doing work or by heat flows. You can let heat flow into the box and the internal energy increases. You can compress the box by doing work and the internal energy increases. Alternatively, heat could flow out, or the gas could expand the valve across a distance and do work on the outside world. But whatever happens, the energy is always conserved, and it always must be in one of these three forms. If heat flows out of the box and you're not replenishing it with work, the gas must be losing internal energy. If you do work with no heat flow, the internal energy must increase, and so on and so on. So you might be thinking, okay, is there really a difference between heat and work if they're both forms of energy, and if they're both transferred by speedy molecules crashing into walls and so on? It's a fair point to make. Heat and work are really both kinetic, movement energy in molecules. But in heat, this work is disordered. The directions of the motions are random. When you heat the gas, everything moves faster, but there's still no overall direction. But when you do work, you're pushing in a specific direction. The molecules will start to move more in that direction. The distribution will be biased. Hence the distinction. Heat, then, is the flow of kinetic energy of these molecules from hot places, where the molecules have lots of energy and move quickly, to cold places where they don't. This energy can flow by physical collisions, as in conduction and convection, or by radiation that passes between the molecules. The first law of thermodynamics, as well as being incredibly useful, has one super important consequence. You can't create something from nothing. In other words, you can't win. You can't create energy. For almost as long as humans have been tinkering with devices, they've dreamed of a potential perpetual motion machine. The idea is simple, and it's part of this broader deceptive concept in technology. Just because something's easy to imagine does not mean that it's easy or even possible to realise. So they dream of something that can either generate energy from nothing to continually move, or else something that's a perfect store of energy, with no friction at all, that doesn't dissipate. So maybe you think to yourself, I don't know, the planets in their orbits, for example, they seem to be a perfect store of energy. They continue rotating around forever. But in actual fact, they suffer friction-like effects too, due to things like the stellar wind of particles from the sun pushing on them, collisions with the sparse matter in outer space, and eventually gravitational waves and radiation. The laws of thermodynamics forbid perpetual motion machines. The first law says that you can't have a perpetual motion machine of the first kind, which creates energy out of nothing, because energy is conserved. And the second law bans the other kind, where energy is perfectly stored. So truly in thermodynamics, you can't win. And that old Simpsons joke where Lisa builds such a machine and Homer yells at her, "Little lady, in this house we obey the laws of thermodynamics," it totally works. Not that people haven't spent ages and ages and ages trying. Now, I got so far into the weeds on this, and so much enraged by looking at all of the different free energy scams that people have perpetuated throughout the years, that we're actually going to do a whole bonus episode on it at some point, and I hope you guys will enjoy that, because I found it very entertaining to research all this stuff. But basically, lots of people have tried to build perpetual motion machines using all kinds of techniques. Many inventors, especially before thermodynamics was really understood, thought that magnets were producing energy from nothing. You can see why too, right? I mean, put two magnets close together and they fly across the room towards each other, as if they're pulling kinetic energy out of the sky. And of course, insane clown posse, those famed philosophers and scientists, were also concerned with magnets. How do they work? So they look like they're pulling energy out of the sky, and in a sense that's exactly what they are doing, because the energy is stored in the electromagnetic field, which is set up in a particular way, because of the configuration of the magnets. But you can't use this to produce limitless energy. And you can see why, right? If you want to produce more energy, you need to pull the magnets apart again, do work on the system, so energy is still conserved. It's a little bit like saying that you can use gravity, and lots of perpetual motion machines did rely on gravity. But you can see that if you lift up an object and then allow it to drop down again, you're not producing more energy out of that system. In actual fact, this kind of thing will lose a little bit of energy due to air resistance and friction and so on. So when you lift up the object and release its energy again, the energy that you put into it by lifting it up, you don't get more out. So there are examples of people who tried to fool this before they realised what was going on, where you have complicated arrangements of water in buckets that tip over and rotate a wheel. The problem is that we can see there's always some energy dissipated. When the water hits the bottom of the bucket, for example, it generates some heat that leaks out into the atmosphere. And there's also usually some friction in the wheel, so these things can't go forever, even if they can go for a long time. There are an amazing number of different designs for this, from engineers and inventors across the world, from Bhaskara to Leonardo da Vinci. Some of these contraptions can be well designed and can move for quite a long time, but perpetual motion is impossible. Most of the most convincing people who've tried to achieve it have had some dirty secret. There's a man behind the curtain frantically pedalling to drive the wheel, or a massive secret array of hamsters spinning in wheels to power the device, or the whole thing is just an elaborate con and they never let you measure it properly. The Royal Society banned all future proposals for perpetual motion machines back in 1775, probably sick of figuring out the various ways that people had tried to break the unbreakable laws of physics. Despite this, people have been claiming to have these machines since the dawn of time, and they still do. Nowadays, they'll usually dress up their claim by pointing to some random aspect of physics, like the often misunderstood zero-point energy, or waving their hands and saying quantum oogly boogly, but it's the same old nonsense every time. A notable example recently was the Motionless Electromagnetic Generator, or MEG, built by Tom Bearden. Allegedly, the device can eventually sustain its operation in addition to powering a load, without applying any more external power, and Bearden claimed that there was some vacuum energy being extracted from the immediate environment, but this is ridiculous. If you work out the density of this quote-unquote quantum vacuum energy, you realise that you need to have detectors the size of the whole world just to boil an egg, and it gets ridiculous. So, science writer Martin Gardner said about this that his physics theories, compiled in the book that he published himself, called Energy from the Vacuum, are considered howlers by physicists, and that his doctorate was obtained from one of those dodgy colleges that you send away and get as many degrees as you want from. Alongside this, and amazingly in my view, there was Storn Limited, who claimed that they'd built a device based on rotating magnets in 2009 that could generate more power than it took to run it. And they even solicited scientists to test their claims. With a lot of swagger, promising a revolutionary source of clean, free energy, they managed to attract an incredible €23 million in investment. But a public demonstration was cancelled at the last minute due to mysterious technical difficulties. The jury of scientists said that the technology just didn't work. Amazingly, they continued to pull this stunt after being publicly rebuked by scientists and failing to demonstrate their technology on the world stage. In May 2015, Storn put an Orbo power cube on display behind the bar of a pub in Dublin. The power cube was a small box, which the pub website claimed contained a perpetual motion motor, which required no external power source. Yes, that's right. Apparently at this stage they'd had perpetual motion technology for 7 years and they were using it to charge phones. And of course the thing was powered by a battery. So the whole thing was an elaborate con, not even an original one, and in November 2016 the company went into liquidation after stringing along the gullible and the people who didn't believe in science and squeezing every last drop out of them. Last I heard, and I actually spoke to someone who knew him, the founder is now making a living as an online poker player, running a website that also seems like a very thinly veiled scam. Ironically, I guess they did make something from nothing. They had no workable technology and they made €23 million from it. All I will say is that if you don't believe the laws of physics, you have to believe the obvious reality that any person who successfully developed a perpetual motion machine would be ludicrously wealthy and many of the world's problems would be solved. I guess they just don't work. It's amazing that more than 200 years after the Royal Society said perpetual motion could never happen, people still fell for it and they still fall for it today. It almost makes me think, gosh, what am I doing being a science communicator and studying physics when I could just try and sell people a scam by going quantum oogly boogly and make loads of money? But, I guess I'm too nice to do that. And I don't think I could get away with it without a straight face, to be honest. So if someone tries to sell you a perpetual motion machine, do not buy it. Obey the laws of thermodynamics. Not because you want to, but because you have no choice, like the universe itself. Thank you for listening to this episode of Physical Attraction. You can't win, but I hope you had fun finding out why. So now, time to reel off all of the many different ways that you can find and engage with us. We are on Facebook, Physical Attraction, Facebook page. We are on Twitter at PhysicsPod, often getting into overtly political arguments with people and retweeting all sorts of interesting articles I found about science. One thing you might want to do is go and listen to the archives of Hugo's There, because if my calculations are correct, then my episode should be released there, about Gateway, a sci-fi book that I reviewed. That's very good. And you can engage with us on www.physicspodcast.com. That is where all the episodes are published. There's a full archive. You can find a link to donate a little bit of money if you want to help us out. And in exchange for that, if you give us just $3, then we'll give you the bonus episode on aliens, which was quite an amusing episode. And there might be more bonus episodes out there by the time I release this, so you'll have to see. You can subscribe to us on Patreon and get the similar things, but with, a more Patreon-y package, I guess. But the PayPal link is always there if you want to help us out. And if you don't want to do that, the best thing you can possibly do for us is just tell one friend, because, as I continually say, if every listener tells one other listener, then before long, exponential growth will ensure that we have billions upon billions of listeners. And at that point, presumably, I will take over the world. Until then, don't waste your time trying to build a perpetual motion machine. Just eat a piece of toast and watch the evening news. We'll be back next episode with the second law of thermodynamics, and no Mew songs. Until then, stay safe.